The system of measurements that the vast majority of the world uses is based on a lump of metal in Paris, and its changing mass. Wait, what? The entire metric system is defined from just 7 base SI units: the metre, the second, the kilogram, the Kelvin, the ampere, the mole and the candela. Almost all of these are based on unchanging physical properties of the universe. For example, a metre is the distance light travels in a tiny fraction of a second. The kilogram, however, is different. The kilogram is defined to be equal in mass to a cylinder of platinum and iridium stored at the International Bureau of Weights and Measures on the outskirts of Paris, and it's called the International Prototype Kilogram, or IPK for short. The first problem with this is that it is hard for scientists and manufacturers around the world to generate a value for the kilogram when needed. With the right equipment, it is easy to see how far light travels in a given time to generate a value for the metre. But unless you can check the mass of your object against the mass of the IPK, you have no way of knowing that it has the mass you think it has. So that's what happens, almost. The IPK has 6 sister copies stored with it, and 10 copies stored elsewhere for routine use. The copies elsewhere are then used to create hundreds more copies, which are sent around the world. The copies in each country are then copied again and distributed to scientists and manufacturers within that country. They then have something to measure the mass of things against that they know to be exactly correct, provided that there are no errors in copying. In other words, everything you buy that has a given mass has been measured against a copy of a copy of a copy of the IPK. The issue with this is that it necessitates the creation of a lot of kilograms, but that's not the most troubling issue with the IPK. The second, and perhaps most severe issue with the IPK, is that it is changing mass. The IPK and all of its replicas are stored in air rather than in a vacuum, meaning that a variety of issues, such as oxidization and contamination, can occur, causing the IPK to gain or lose mass. The mass of the IPK varies by as much as 116 micrograms compared to K4, a replica stored in the USA created in 1889. This may not sound like much, but it can make a huge difference. An example is when calculating the number of atoms in a substance. A precise figure for this can be useful when calculating the yield of a chemical reaction, which can be important in many fields of science and manufacturing. The change in mass of the IPK by 116 micrograms means a change in up to around 7 quintillion atoms, which is a number far beyond the scope of everyday use. The difference can also be problematic when dealing with extremely large masses as well as extremely small ones. The mass of the Earth is 5.9722 septillion kilograms. The instability of the IPK means that 5.9722 septillion kilograms varies by as much as 690 quintillion kilograms from the true mass of the Earth, which is rather a lot. It is worth noting at this point that the value assigned to a mass of the IPK does not vary. Definitionally, it is always a kilogram. The value of the kilogram itself grows and shrinks with the IPK. The value assigned to the mass of all other objects then changes, despite the thing with the changing mass being the IPK. It's not just mass that this affects. 3 base SI units, the mole, the candela and the ampere, are all defined in terms of the kilogram, as well as a vast amount of other SI units. For example, the Newton is the amount of force required to accelerate 1 kilogram by 1 metre per second per second. The joule is the amount of energy required for a force of 1 Newton to act over 1 metre. The watt is the amount of power corresponding to 1 joule per second. The volt is the amount of potential difference equal to the power in watts divided by the current in amperes. The ampere itself is defined in terms of the Newton, as is the SI unit of pressure, the Pascal. When the kilogram changes, so to a vast array of other measurements. It is not difficult to see why this may be a major problem for modern science. Clearly, something has to change if science is to continue to progress. Unfortunately, there are people working on that. The International Committee for Weights and Measures voted in 2010 to pass a resolution acknowledging the intention to define the kilogram in terms of the Planck constant. However, no such definition has been officially adopted by any organisation as of 2016. The two other main schools of thought about how to define the kilogram involve either opposing the weight of a kilogram with an electrical current and using that amount of current, or power in case of the watt balance, to define the kilogram, or stating that a certain number of atoms of a given isotope of a certain element is equal to the mass of a kilogram. There are several rival proposals on how to do this, the two largest involving carbon-12 or a mix of different isotopes of silicon. Both of these approaches have the same problem. Generating an accurate mass of a kilogram on demand in a scientific laboratory would require that laboratory to have a completely accurate way of measuring acceleration due to gravity at that specific location, so that they could turn a very precise measured weight into a very precise measured mass. Ultimately, no way of defining the kilogram is without its flaws, and there appears to be a barrier of bureaucracy in establishing a new definition anytime soon. So, for the time being, it looks like the scientific community might have to put up with an inconsistent kilogram, or at least it will do for the next few years. That's the IPK, and this has been Weight What?